Hello, good evening, everyone. My name is Dr. Mohit Arya, Assistant Professor from IIMT College of Science and Technology. So today I will explain the linear dependence and independence of vectors, variables, consistency of equations in matrices. Okay, first we will discuss about the linear dependence and independence of vector. If there are some vectors, say x1, x2, x3 and up to the n vectors are said to be linearly dependent if there exists some scalars with respect to these vectors. Suppose if there are four vectors x1, x2, x3 and x4, then the scalars will be lambda 1, lambda 2, lambda 3 and lambda 4. So which means if there are n vectors, then there must be n scalars. If there are 7 vectors, then there will be 7 scalars, such that the multiplication of first scalar and first vector plus the multiplication of second scalar and second vector up to the same as up to the nth scalar and nth vector should be equal to 0, where not all lambda I not equal to 0, otherwise they will be linearly independent. We will understand this definition with the use of an example. Here example says, examine the following vectors. There are 4 vectors are given. We have to examine these vectors are linearly dependent or not, or if they are, then find a relation between them. Then here we see that there are 4 scalars. We will consider there are some scalars lambda 1, lambda 2, lambda 3 and lambda 4 with respect to these 4 vectors. Then according to our definition, what we will do, we will multiply each and every scalar with a vector, and then we will add all of these and equate to 0. This is an equation. Okay, so now we will write this equation with the use of these given vectors. Those are x1, x2, x3 and x4. These all 4 vectors. What we see that lambda 1, the first vector 1, 2 and 4, second vector 2, minus 1, 3 with the scalar lambda 2. With this scalar lambda 3, there is the third vector 0, 1 and 2, and with scalar lambda 4, that is another vector will be minus 3, 7 and 2. So here what we say, we will convert this particular equation in the form of system of equations. This system of equation will be directly related with the assumed scalars. These scalars are lambda 1, lambda 2, lambda 3 and lambda 4. The equation is being converted by using, we will multiply lambda 1 in that first element of the vector x1. There will be lambda 1 into x1, that is lambda 1. The another will be lambda 2 when multiplied by 2, the first element of the vector x2. So that will be 2 lambda 2. Similarly, when we will multiply the lambda 3 with the first element of the vector x3, we will get 0 multiplied by lambda 3, and here when we multiply the first element by the lambda 4, we will get minus 3 lambda 4. So similarly, we will form a system of equation, which is now the system of equation is the form of Ax equal to B, where E is called the coefficient matrix, X is called the matrix of vectors or matrix of some variables, and V is the constant matrix. So here we see in what we see, if we write the coefficient matrix, so what we take each and every coefficient of lambda i's in the form of matrix entries, such as if we are taking A11 of a matrix, here we see in the first phrase the Ax equal to B form is like this. Here A is our coefficient matrix, X is our what are the matrix of variables, and the another is our constant matrix. So if we are talking about the first entry A11, second element A12 and nth element A1n, these elements are nothing but the coefficient of our variables. So here we see that A11 is the coefficient of first variable, A12 is the coefficient of second variable, A13 is the coefficient of third variable. With the help of this concept, we write the entire equation in the form of Ax equal to B, that is our equation number 1. Then what we do next? We consider the vector, the matrix A. we will consider this matrix. The matrix is coefficient matrix. We consider the matrix A. Now, with the help of elementary row transformation, we convert this matrix A into a upper triangular matrix. Okay, so we applied some operations. We changes in the row 2 and we change in the row 3. So we change in the second row such that we take all the elements of second row has been subtracted from the 2 times of the all the elements of row first. Okay, and similarly we use the second operation, so we get a transform matrix, that is this, the matrix this. Okay, and again we will apply another operation, that is we change in the row R3, we change in the row R3, that is third row. Okay, such that we subtract all the entries of row R3 from the second row. Okay, so now using equation 2 and equation 1, we will use equation 2 and equation 1. We get this particular equation 1 such that now what we do, again we convert the system of equation in the form of again we consider this matrix system in the form of system of equations. So this will be our required system of equations. Now there is a note, when we solve this system of equation, we must need the number of equations equals to the number of variable. If the number of equations are equal, if there are 3 equations, then number of variable must be 3. If there are 3 equations and number of variables are 4, then in that case we must have to consider at least one variable as a free variable. So here we consider the lambda 4 equal to k, which is a free variable. Then lambda 3, by using this equation, then lambda 3 will be equals to minus k, and with the help of lambda 4 and lambda 3 we will find out lambda 2 and then lambda 1. Okay, so these vector will be linearly dependent because none of the lambda I is equal to 0. The main condition for an equation to be linearly independent is each lambda I should be 0. If one of the lambda I is not equal to 0, then the system of equation or the given vectors will not be linearly independent. Next we see that now the another part, if we have to write the particular solution of the given problem, then what we do, we will put all the values of lambda 1, lambda 2, lambda 3 and lambda 4 in our the first equation, that was lambda 1 x1 plus lambda 2 x2 plus lambda 3 x3 plus lambda 4 x4 equal to 0. This is our first equation. Okay, so then when we put all the values of lambda I, we will get the desired solution. Okay, so we can simplify it and we can get the solution. Next, the point is linearly dependence and independence of vectors using rank method. Previously what we have done, we just use the matrix method and we find the linearly dependence and independence of vectors by using the lambda introduced parameter, and if one of the lambda I is not equal to 0, then the vector is linearly dependent, otherwise it will be linearly independent. Okay, we will move forward. We see that if the rank of the matrix of the given vectors is equal to the number of vectors, then the vectors are linearly independent. The second point is that if the rank of the matrix of the given vectors is less than the number of vectors, then the vectors are linearly dependent. Okay, we will see that with the use of an example. So here we are having 3 vectors. We have to check are these vectors are linearly independent or dependent. Okay, so we have to show in this particular question, we have to show that these given vectors are linearly dependent. So what we do, here we consider a matrix M. Okay, we consider the matrix M where each row is the entry of these particular given vectors, where 1 2 minus 3 4. Okay, this is the first row and first vector, and 3 minus 1 2 1, this is the second row and second vector. 1 minus 5 8 minus 7, third row and third vector. We will apply some operations and convert and find the particular rank of this matrix. The operations applied here R2, we will change in R2 the second row such that each element of second row has been subtracted from the 3 times of R1. Similarly, we will apply the operation in R3. We will get the modified matrix. Okay, this is the transformed matrix by using the elementary row transformation method. Similarly, again, we apply the elementary row transformations and we will get the our desired matrix. Here, the rank of a matrix is the number of non-zero rows. Okay, when we transform the matrix, when we get the number of non-zero rows, then this particular number is called the rank of that particular matrix. So here the number of non-zero row is 2, therefore rank of matrix M is equal to 2. Here number of vectors are 3. So here we see that the rank of M is less than the number of vectors, therefore the given vectors are linearly dependent. So in 10th class, we have studied the consistency of equations. We have the system of equation in two variables, where a1x plus b1y equal to c1, a2x plus b2y equal to c2. Okay, so this is a simple given system of equation. We must have aware about it. What we see, this system of equation will have a unique solution, or this system of equation will be consistent if a1 upon a2 is not equal to b1 upon e2 is not equal to c1 upon c2. Then the system of equation will have infinite many solution or infinite number of solutions, means the system of equation will be consistent if a1 upon a2 equals to b1 upon b2 equals to c1 upon c2. But the system of equation will be inconsistent, means it will not have any solution in such a way a1 upon a2 will be equal to b1 upon e2 but not equal to c1 upon c2. So this is a 10th class concept. Okay, so now if we talk about the consistency of system of equation, if there are n variables and particular m equations, then what will we say about the consistency of these equations? So system of m equations using n variables. Okay, so here what we did in previously, if we particular having the system of equation of two variables, okay, then what we do, we will make the coefficients same either of x or of y. Here we are making the same coefficients of x, then what we get particularly a system of equation where we can, when we subtract these equations from each other, we get the solution of the particular equation. But here what we see, the writing the aforementioned system of equation in a matrix form. The aforementioned system of equation where m equations using n variables. So we write it in the form of ax equal to b, where a is the coefficient matrix, x is the matrix of variable, and b is the matrix of constants. Now we will make the augmented matrix. The way to make the augmented matrix is that firstly all the entries of coefficient matrix, and then we will include one more column, okay, with all the entries of the constant matrix. This matrix will be of the order of m cross n plus 1, and the particular matrix is called the augmented matrix. So the point is that an augmented matrix is a combination of all the entries of a matrix A and matrix B. So here we see that all the entries of matrix A we have taken here, and all the entries of matrix B we also have taken here. So now the question arises that how can we say that with the help of augmented matrix the system of equation is consistent or inconsistent? The most relevant question. So for consistent equations, if the rank of coefficient matrix and the rank of the augmented matrix, okay, and the number of variables are n, okay, we have find out the rank of coefficient matrix, we again find out the rank of augmented matrix, and then we are having the number of variables, and then the system of equation will have the unique solution if the rank of coefficient matrix, rank of augmented matrix, and number of variables are equals, same. Will have infinite many solution if rank of a matrix of coefficient matrix, rank of the augmented matrix is equal, or will be system of equation will be inconsistent. In that case, if rank of A is not equal to rank of C, we have clearly understand that the rank of A means the rank of the coefficient matrix and rank of augmented matrix. So here is an example. Show that the equation, these are some equation given. The equations are given in the three variables x, y, and z. Okay, we have to check this system of equation is consistent or not. What we take, we are taking this particular system of equation. Okay, we write the system of equation in the form of ax equal to b. Now what we do, we will take the augmented, we will make the augmented matrix. In augmented matrix, as usual, as I said before, we have taken all the entries of the matrix A, then we include a particular column which is the matrix B. So we have included it. So when we apply the elementary row operations, we will get the transformed matrix. Now here we see that this particular portion is of the matrix A, and this particular portion entire is the matrix C. Okay, so here we see that the rank of A, if we see this transformed matrix we obtained with the use of matrix A. Okay, so here we see that the rank of this particular system is what? Is 2, because the number of non-zero rows are 2 here for the matrix A. But for the entire augmented matrix, the transformed matrix, in the transformed matrix, there are number of non-zero rows are 3. Okay, so here we see that the rank of A is equal to 2, rank of C equals to 3. Clearly, rank of A is not equal to rank of C. Therefore, the system of equation is inconsistent. As we discussed before, if rank of A is not equal to rank of C, means rank of the coefficient matrix is not equal to rank of augmented matrix, then system of equation will be inconsistent. Next we say, test the consistency of the following system of equations and hence find the solution. So what we can see here, this is a system of equation given in three variables x1, x2, x3. What we do, we will find out the augmented matrix. Augmented matrix means here we are having the particular matrix, coefficient matrix, and we have introduced another column for the matrix B. So here we see, we apply again the elementary row transformations and we got a transformed matrix finally. In this transformed matrix, there are two parts. One part is of the matrix A and another part is of the entire matrix. Okay, by including matrix B. Here we see that there are the number of non-zero rows in matrix A are 3, and similarly the number of non-zero rows in matrix C are also 3, and the given number of variables are also 3. These are x1, x2, and x3. Therefore, the solution will be unique. Hence, the system of equation will be consistent. So here we see Ax equal to B. Our system of equation Ax equal to B can be written by using this particular matrix A, the transformed matrix using A. This is also an upper triangular matrix. So what we have done here, we just write the entire system Ax equal to B in this particular form. Now the B, by modifying, by transformed using row transformation, elementary row transformation, or transformed B is here. So when we solve this particular system of equation, we will get the value of x2, x3 equal to minus 32 by 15. The value of x2 will be 12 by 19, and the value, the value of x2 will be minus 4 by 15, and x1, the value of x1 will be 44 by 15. Now we will talk about the system of non-homogeneous equations. Okay, a system of equation is said to be non-homogeneous if it is of the form of Ax equal to B. So in previous slides we have discussed about the system of non-homogeneous equations. Okay, now in this particular scenario we will talk about the system of homogeneous system of equation. So what it says, for a system of homogeneous linear equation Ax equal to 0, x equal to 0 is always a solution of this particular system of equation. That has been written in this particular form. Another means x equal to 0, y equal to 0, z equal to 0 will always be the solution is called null solution or trivial solution. Another part, a homogeneous system of equations is always consistent. Okay, since a homogeneous system of equation are always consistent, therefore they will have either unique or infinitely many solutions. So for example, we have taken an example. Okay, this is a system of equation. Okay, if we put x equal to 0, y equal to 0, z equal to 0, then there will be an equivalence relation, that will be 0 equals to 0. So it means that the particular, if all our variables are 0, then this will be the solution always for a homogeneous system of equation. The second point is, if rank of A equals to number of unknowns, the system has only the trivial solution. Okay, if rank of A less than number of unknowns, the system of equation will have infinitely number of non-trivial solution. Or if rank of A equal to rank of C, here you have already understood that C is the augmented matrix. The system of equation will have infinitely many solutions. So this is the all we need, all we have. So we have explained all about the system of equations, we have explained all about the consistency of equations, okay, and how to solve them. So this was the part of the matrix theory. So this is all from my side. Thank you very much.